attendees. Shukran for the invitation to present at the first conference of engineering and science and technology. My sincerest apologies that I'm not able to be with you. Hopefully in the future, if an invitation comes again, I would be in the position to attend. Looking at Table Mountain from the opposite side of the bay, that UCT is actually on the left-hand side of the mountain, just around the sort of edge of that mountain on the slope. Let me start by giving you a little bit of background to where we are with the university and the work that I'll be talking about, title being Synthesis and Application of 6-deoxy 6-amino chitosan, which is, of course, material which is derived from the fishing industry waste. This is the slope that you've seen from the previous picture. There's that view around that, bend. You can see sort of on the slopes here. That's where the University of Cape Town is, and from a different view, head-on view, there's the campus, and a little bit closer, you can see there, just below what is called Devil's Peak. We've got about 20,000 plus students at the university, and we've got basically all the different disciplines. Obviously, there's not enough space, and there's a great demand for students to for space to increase the size of the university. But we'll see how that will go in the future. In the Western Cape and in South Africa, in the Western Cape particularly, we have lots of fruit, wine industries, table fruit, citrus fruit, and of course we have see the beautiful beaches and of course these fishing industries. Then if you go a little bit up further north on the east coast, in the KwaZulu-Natal, Durban area, we have sugarcane, and of course inland we have lots of game parks, and also on the coast as well. And of course in the Gauteng northern part of the country, mining, coal, diamonds, platinum group metals, these are all the different resources that we have. My focus of my work is particularly the waste produced in the fishing industry, and perhaps also to some extent waste derived from the agricultural industries. Now, the University of Cape Town, we trying to increase our contribution in science towards sustainable development, and particularly working in line with the government initiative to create more jobs in the green sector. And there's a lot of support for that, through even loans and development back for pushing technologies all the way through to commercialization, and in that way creating small companies and jobs. From a biorefinery concept, if one looks at food, particularly food waste, solid food waste, we globally we only utilize about 1/3 of all farm produce. The rest is just basically waste. So that waste can be both solid or within liquid form when it's washing fruit or whatever processes that has organic materials. And of course, it's not that easy to get rid of organic materials through municipal systems. You need to lower the organic content. So why not look at ways of extracting that organic content and then convert that into valuable products. And of course, one can design your agricultural process to take care of whatever waste material comes, so that we can sort of close the loop on a biorefinery process. Many people would probably be looking at energy production from organic waste and so on, biogas and so on. I'm basically more interested in materials from and polymeric materials that will have specific application that is derived from this particular waste. So if one wants to do valorization of a waste stream, obviously you need to consider that there is enough material to sort of have a sustainable business on that material. So you need to have a byproduct available, enough waste available, and of course your location is also important in relative to where that waste is generated. Of course, it must have a compositional value which you're going to tap into, and of course it helps to have a very well-defined market for that particular material that you envisage to make. Chitin, which is the source of the waste source that we're interested in here, is obviously the second most abundant polymer, natural polymer on the planet. You can see everything, every structure of exoskeletons of insects and arthropods, plants, and many other mollusks, and also then we can look at fungi, mold, yeast. They all need chitin for structural support. So there's an abundance of that, and we focus now basically on the supply from insects and crabs, arthropods, and of course that which comes from plants and biomass waste. Chitin and chitosan, how do they differ from your normal glucose? Glucose, yeah, the structure of glucose, or this is the glucose monomer that gives you cellulose, beta 1,4 linkage. So if you take the 2-hydroxy away and replace that with an amino group, then we have chitosan, but that's not so much. Naturally, the structural material is chitin, which is fully acetylated on the 2 position in nitrogen. And as you deacetylate this chitin, this is highly water insoluble. So as you deacetylate this, it becomes a slightly more water soluble, but not much. And we are particularly interested in water-soluble materials. Chitin and chitosan is well known and well studied, and many applications already exist. But we are basically interested in modifying further so that we can get higher water solubility and also other specific functions. And that's what I'm going to be talking about. The supply of chitin, you can see the breakdown of the as a composition of the dry weight. You see chitin is highest in shrimp and fungi, but obviously mushroom and fungi, you don't have a good waste supply. You eat the whole mushroom. Maybe if you're lucky, then you'll get some bad quality mushroom, but the amount, the numbers is not as much as in for crawfish and shrimp. These are large tonnages of 100 to 1,000 tons per year in our regions here as well. So much more than what we really need in order to have a sustainable business. Then lower amounts come from insects, and but of course the main supply is from shrimp and crawfish. Lipids also, but not that much. So basically we're interested in the chitin supply. So yes, why chitin or chitosan? It's biocompatible, it's biodegradable, it's non-toxic, it has the ability to be functionalized. If you look at the structure of chitin, you get a reactivity could be higher at 6-hydroxy and maybe a little bit lower at the 3. And of course, if you look at chitosan, you will have selective reactivity of the more nucleophilic nitrogen versus your hydroxy group here. It's non-toxic. It's got a, definitely ability to be selectively functionalized. It's obviously renewable and it's abundant. If one looks at the origins of it, could be, as I've mentioned earlier, primary food waste or secondary food waste or incidental food waste. It could be planned around a particular process of making some particular, growing prawns or aquaculture of prawns, for example, more control. So you can have very clear idea of how much shells you're going to get. And then, of course, we need to convert chitin to chitosan. And chitosan itself has already found widespread use in drug delivery, catalyst, food technology, cosmetic, agriculture, biotechnology, etc. Yeah, some of the products are already in the market. You can mold chitin and chitosan material, polymer, and into particular shapes. It finds its way. It's got good antimicrobial properties, dental products, cosmetics. You can also co-spin that with synthetic fibers, and also you can use it for conditioning of fibers. And there are a product called Crabion, which is a crab chitin derived polymer that's being used for making a textile. And of course, you can 3D print some of the formulations. The bulk application for chitin and chitosan, it's high volume, low cost applications are definitely in the water purification or in the agricultural industry as a plant immune system stimulant and as an antifungal. The world chitosan consumption, you can see that by mass basis, it's almost 50% is goes to the agrochemicals, whereas the other areas, the water treatment area, whereas other areas are growing in the cosmetics and food and beverage. These are slowly growing in size. The different waste materials that food waste that you can get. Again, mushrooms, the black shoulder fly that can live off food waste will produce these pupa, which in itself is very high protein content and also high oil content with a little bit of chitin. And of course your prawn waste and your crab waste. And we've got a lot of lobster waste here, and also some squid pen, which is a bycatch of lobster in the lobster catch industry. So not a shortage of any supply. And of course your Asparagus nigerans can be used to grow on food waste, and then you can harvest the mycelia and also extract your chitin and chitosan. This is where our crayfish comes from. We've got two types basically. The coastal one here in the colder water is this particular one up here, which is it's got more thicker legs, and of course this is it's sold whole live mostly, so it's not a lot of waste from here, but there are some that the tail gets removed and then the body is available for stock and so on. So people can buy that, and the Asian companies buy this waste, and they produce obviously chitin and chitosan amongst other things. We like to barbecue it. The other one is with the spiny legs, so it doesn't have a lot of meat in those legs, so the body is removed, the tail is removed from the body, so there's lots of waste in this one. This one is caught more inland into the sea, in the deeper waters, and most of the work that I've been doing was on waste that's derived from this particular species. This is what we've done in conjunction with a local fishing company called Premier Fishing. So after the catch on the boat, they will split apart the tail from the body. The body gets crushed, comes on land as frozen blocks, and of course the meat can then the residual meat in the legs can be extracted then to produce what we call a lobster stick, and the residual chitin itself can also be extracted with organic solvent to give the color or that orangey reddish color, which is actually a pigment called astaxanthin. So it's got really very good antioxidant properties. Then the chitin is then deacetylated to chitosan, and this obviously, we've done some work in producing catalyst, solid support chitosan is a solid support catalyst. We've done some oil fractionation using chitosan, water purification, and antimicrobial studies. This is just how the Aspergillus niger can be used. We've got a lot of fruit agriculture and apples, pears, those stone fruit, and of canning industry. So they will produce lots of pomace. Up north, in the sugar industry, we have molasses, and of course, fruit peel can come from many of the other agricultural industries. Then Aspergillus niger is known to produce either the chitin as well, chitosan and enzymes and citric acid. So that is just another way of, and of course your other fungi, mushrooms, as I've mentioned earlier, is another way of making. So a local company here we have called Agri-Protein. They are already in full-scale production, making mag oil and mag meal, which is derived from fruit and food waste that's been fed to these maggots and to the pupa, and then what we call here is the black soldier fly is doing this particular work to convert your waste into agriculturally useful materials. Chitin itself very easy to isolate from fungi. Doesn't require very aggressive chemicals. It's basically treated with sodium hydroxide, and you extract that into dimethylacetamide as a solvent in conjunction with lithium chloride, and it's very insoluble in water, so it will precipitate, and then you can isolate and dry it. Whereas with the cell, you need to wash, crush, and then demineralize it, because it's got, unlike the fungi, it's got a lot of calcium biomineralized with the chitin. Then you have to remove the protein with sodium hydroxide, and then you get your raw chitin. These are just companies that are producing chitin, and some that are doing, but go a bit further by making a high quality, high purity medical application chitin and chitosan as well. Okay, so we need to look at our interest is to convert chitosan, which is partial, very, very slightly soluble with that hydroxy there, convert this hydroxy to an amino in a very environmentally friendly and scalable process to produce 6-deoxy 6-amino chitosan, which in turn can then be utilized for cosmetics, drug delivery, catalysts, and biomaterials. Okay. So this is the plan. Before earlier studies, the chitin itself, you first do a base treatment, and sodium hydroxide aqueous that will take care of the acetal group here. Then second step is to protect the amino group with a phthalate group as a phthalate group, and then you want to convert the hydroxy into a better leaving group. So there are many ways of doing that. In this particular way, they've taken a N-bromo or N-chloro or N-iodosuccinamide along with triphenylphosphine to give in N-methylpyrrolidone as a solvent at 80 degrees. Will convert hydroxy to the halo intermediate here, and then you just substitute the halogen for an azide, and then you do a Staudinger reduction with triphenylphosphine, and then you end up with, and of course after deprotection of the pethaluol group with hydrazine, you then have the 6-deoxy 6-amino chitosan, which is completely water soluble. However, in our hands, we could not get the solubilities reported because a lot of the product still has lots of triphenylphosphine oxide in there, making it very hydrophobic, and therefore we could not get solubilities claimed, and obviously we wanted to improve on this process. The solvents used here, DMF and NMP, these are solvents that will be in with the REACH regulation to be limited heavily in the European Union. So we're trying to move away from these solvents to more, sustainable and more environmentally friendly solvents. So we changed the process slightly. First of all, still need to do a deacetylation, and then of course take the deacetylated chitosan, and then protect as the pethaluol, and then you, instead of converting this to the halogen, we found it was better to use tosyl chloride, put it in to produce the tosyl, which then is substituted with the azide, and then reduced to using the Staudinger reduction to the amine. And then, of course, the final step is to remove the pethaluol group to give us the 6-deoxy 6-amino chitosan. We got a much better product. However, it's still not scalable because it still contained quite a bit of triphenylphosphine, and it's not as soluble as we would have liked. So in order to try and get better solvents for the process, we screened a whole number of solvents. We went over to the York University Green Chemistry Center of Excellence, spent some time working on a whole range of solvents, and it happens that dimethylacetamide with lithium chloride combination worked out as the best solvent for the system, and most people have been using that, and there's a lot of research going on to try and replace those solvents with either DMSO, which is more environmentally acceptable, or any of these bio-derived solvents like dimethyl carbonate, lactone, styrene, and so on. These are all new solvents which are more environmentally friendly. So lots of work, and of course ionic liquids. A lot of work are currently going on in trying to replace these solvents here. So we wanted to follow green synthesis, so there were some ionic liquid mediated protection and deprotection. So chitin and chitosan, instead of using sodium hydroxide, you could use this imidazolium ionic liquid to do that deacetylation. And also these were done in microwave. Then to protect the amino group, the pethaluol was, instead of using DMF, we could use acetic acid in water, which is a much more environmentally friendly solvent to give as good results. So now targeting this diamino chitosan, first, of course, we could use either the ionic liquid method of deacetylation or sodium hydroxide. Then protection using acetic acid and a water mixture with pethaluol to put the pethaluol group in there. Then tosylation of the 6-hydroxy in dimethylacetamide, which is a better environmentally more friendly solvent. And then we could do a neat displacement with alkylamines directly from the tosyl to the substituted alkylamine. Ammonia itself doesn't work that very well. You need high pressure sealed vessels, and we opted not to go by that way. So we can also do a tosylation directly on chitin and then do the treatment with an amino or alkylamine to give you the target product. So the better solvent here would then be demaltosylchloride, triethylamine, and lithium chloride to do the tosylation step here. And of course, the substitution with the alkylamine gives you the product. And of course, we still don't use ionic liquids to do the deacetylation. Now we have a process whereby we can take chitin, convert it to chitosan, protect the amino group, tosylate that, and then we switched here from using sodium azide, we use potassium perthalamide as a nucleophile. And potassium perthalamide then substitutes this tosyl group, and all we then have to do is to do a global deprotection like we've done before to remove the perthaloyl groups to give us the diamino chitin. Now this product here gave much better yields, and also we did not have to deal with the problem of triphenylphosphine getting stuck in the polymer. So the solubilities were much greater for our product than that which has been reported. So, and of course, you can do this with chitin itself, get good substitution, and then you can substitute the tosyl with perthalamide, and then deprotect, and you have aminochitin, and then which is much more water soluble in chitin itself, and then of course you deprotect by base treatment, and you get your product. And of course, we can follow this transformation with anhydrous stains the polymer quite clearly. In order to determine which of these carbon signals belong to the perthaloyl and which belongs to the residual acetyl, N-acetyl, we could do solid state NMR of the perthaloyl chitin, which is not water soluble and not soluble in many different solvents. So we do the solid state NMR, and you can see here, if you compare that with this model compound, here you can see the perthaloyl group carbon that comes up around here. It's just about 160, whereas the acetyl, N-acetyl ones comes up a bit higher here. Here's evidence, of course, of material that was made with our process. If you look at the aromatic region, there's virtually no aromatics there, whereas with the previous methods where you used the Staudinger reduction, you get triphenylphosphine impurities here, which is a bit of a problem. So, we can also, instead of converting it to the 6-amino, we can use the alkylamine approach by making tosylate, and then using ethylene diamine as a solvent and reagent. You can substitute that directly, and then of course you can remove the acetyl group, so you get a diamino but with an extended alkyl 6-amino ethyl amino extension here, which in itself is also quite water soluble. So you can either go that way, or then first go to the chitosan, protect, tosylate, and then treat with ethylene diamine, and you can then deprotect your perthaloyl group, so you get your diamine or 6-deoxy 6-amino ethyl amino chitosan, which is water soluble. This work was published in Carbohydrate Polymers. So the improvements here is the original method to use 6 steps. We narrowed down to 3, used an halogenated intermediate, which is not very green. We went for the tosyl. Some of the hazardous solvents used DMF, NMP. We switched to DMAC, which is less toxic. And of course, earlier work, very few analytical methods we used to characterize it. We've done a much more rigorous characterization of our, and of course, work has been patented as well. We've now taken this 6-deoxy amino chitosan and done some work on, as a catalyst support, antimicrobial, um, and people, and also what's a process called argentation, which is a separation of unsaturated versus saturated fatty acids. Earlier work has been applied to gene transfection. This is a really good gene transfection reagent. And of course, the antioxidant effects have been reported. Drug delivery is very common. Cell growth is also, these are all still areas where there's lots of potential for growth. So as a catalyst support, we published a catalyst, which was a palladium supported catalyst. And this catalyst could do Suzuki, Miura, and Heck cross-coupling reactions in aqueous or alcoholic water mixtures. And also the catalyst was much more stable than as a heterogeneous catalyst compared to the equivalent homogeneous catalyst. Um, and we could get really good yields and very good turnover numbers uh, reactions. And of course, you can, with chitosan, you can do a surf-based link of the ligand. And then once you've got the ligand, then you can put the um, complex on there. And of course, once you've complexed, you do use this as your catalyst, and you can try and repeat that cycle. For we found that it for up to 4 or 5 times, we still didn't lose a lot of it. Then if you make the time, you can double load by a shift base and a reductive amination. You can then immobilize the ligand and then load the catalyst, metal catalyst onto that support. And of course, this gave us very good Heck reactions in aqueous and organo, sort of alcoholic aqueous media. And this was also, applied for different types of catalysts, pyridyl amino as well, and phosphine. And then also the same work was applied to rhodium catalysts, making rhodium catalysts, and we did hydroformylation work on it. Works very well. Also very stable catalyst. Can also undergo quite a number. And then this is the argentation. Argentation is basically you take your polymer, put sulfonate groups on there, and then you load it with silver. So chitin serve that purpose well. And then if you pass through a mixture of fish oil, for example, these oils have saturated and unsaturated fatty acids. So the unsaturated fatty acids will be retarded by complexing with the silver, and the more saturated ones will move faster. So one can get very good separation of saturated, which is cosmetically more useful, and versus the unsaturated one, which can be used as antioxidants for nutraceutical purposes. So we've made quite a range of diamino derivatives which have good antimicrobial activities, and some were used as ion exchange resins for water remediation. These polymers also have a charge, so they were very good in antifungal properties, and it's currently undergoing tests to check its ability to improve crops. As you can see here, it's the diamino versus the chitosan with 0.5 and 1%. You get complete inhibition of the fungus that's responsible for rot in maize. So also this material is quite easily water soluble, whereas the chitosan is not. So this is definitely a big step towards making commercially available material. And we've done some coatings on strawberries. It does increase the shelf life by at least 3-4 days by just spraying coating of Deoxy 6 amino chitosan on there. You obviously can't spray with chitosan because it's extremely viscous, this material, and your maximum concentration you can get in acetic acid is 1. We've also tried some spinning, electrospinning of this material, and then loaded with silver and showed that it is also antimicrobial forms. So basically, in conclusion, we have a challenge here to look at very heterogeneous biomass, which may be subject to seasonal variation, to stable products for which there's a commercially interesting market, which is what we would like to exploit as new products, and look at increasing profitability for farmers and for fishermen, fishing companies. Of course, from an environmental point of view, we're diverting what would have been bio waste going to landfills, we're diverting it to useful materials. We're creating jobs. And finally, I'd like to thank some of the people who worked on it. Shakila Shade, who recently qualified with a PhD, and also Benathile Makubela worked on catalyst work, and she has now moved on also to another university where she's a lecturer. Thank you very much for listening to me. Hopefully next time the second meeting would be there in person. Shukran. Assalamu alaikum.